Okay, so imagine this. Everything around you right now, the stars, the planets, your body, even the tiniest atoms inside your cells, all of it might be standing on something that doesn't actually exist. I know. Wild, right? You're probably thinking, this sounds like some random theory from a physicist who's had too much coffee. Maybe just numbers on a whiteboard that don't mean anything real. But here's the thing. This is real, and it's been real for a while now. Deep inside atoms, in a world so tiny our normal logic just breaks, crazy stuff happens. Forces move between things without touching. Particles affect each other from far away, like they're texting each other somehow. Scientists were confused for years trying to figure this out. Then they found something weird. There are these mysterious things that pop into existence and disappear instantly. Nobody can see them or measure them, but they're literally the reason the universe works. These things are called virtual particles. They're not real in the normal sense, but they control everything that is real. The empty space we think is empty? Physics says nah. It's packed with energy. Stuff constantly appearing and vanishing, like space itself is alive. That's when we realized that nothing isn't always nothing. Sometimes nothing is actually the foundation for everything. What scientists made up as just a math trick turned out to describe reality perfectly, like scary level perfect. We're talking precision down to 1 in a trillion. Think about that. Math based on things that don't exist explains the real world better than anything else we've got. So here's the big question. Did the illusion become reality? Or do we just not understand what reality even means? We keep saying virtual particles, and it sounds cool and mysterious. But what does it actually mean? On the surface, it's simple. But underneath, it's one of the weirdest ideas in modern physics. Picture watching a soccer game, but the ball is invisible. It doesn't exist, yet all the players are running, passing, dodging, and shooting, like the ball is totally there. Sounds insane, right? But that's exactly what happens inside atoms. In that tiny world, empty space is never actually empty. And what we see isn't the full story. Virtual particles aren't physical things like electrons. Nobody's ever seen one. No machine can detect them because they appear and vanish faster than anything can measure. They only exist in equations, like math ghosts moving between numbers. But their effects, super real. They control every interaction in the entire universe. Here's what confused everyone. How do two electrons know to push each other away when they're not even touching? How does the force travel between them with no visible connection? This messed with scientists' heads for years, until this American genius, Richard Feynman, showed up in the 1900s and thought about it differently. Feynman invented a clever way to visualize interactions called Feynman diagrams. Not just drawings, a whole new language for physics. His idea was this. Every interaction between two particles has lines showing the real particles we can see. But between those lines, other lines. Those are the virtual particles, acting like delivery drivers, carrying messages between the real particles. When two electrons push each other away, they're not magically sensing each other. They're throwing virtual photons back and forth, light particles that exist for a split second to carry the force, then disappear like they were never there. They borrow energy from empty space for this super brief moment. It happens so fast that even the laws of physics basically blink and miss it. The beautiful part is this. Even though these particles are virtual, we can calculate their effects with insane accuracy. When scientists used them in math, the results matched real lab experiments perfectly, like measuring the Earth and being off by a hair. We're talking 0.01 parts per trillion accuracy. We're working with something that doesn't exist, but it makes our calculations work like they're describing reality itself. This opened up a huge question. Can math imagination be more real than actual physical experience? Or is the universe really full of hidden things moving in the background that we just can't see? Feynman used to say something important. Don't ask if virtual particles actually exist. Just calculate and look at what happens. But when the results match nature this perfectly, the question refuses to go away. Did we invent an idea to understand the universe? Or did we discover something that was always there, waiting to be noticed? Right here, the line between illusion and reality gets blurry. Virtual particles act like the invisible foundation holding up the laws of physics. Without them, no atoms, no light, no life. Let's ask a simple but weird question. How can something that doesn't exist let math predict reality with ridiculous precision? If virtual particles are just illusions in equations, why do calculations using them come out correct every single time? This is the miracle of modern physics. But how does an illusion work this well? Virtual particles aren't objects. They're symbols in equations describing the exact chances of every interaction in the universe. And every time these equations are tested in a lab, reality matches them completely. Like reality itself is saying, yeah, this illusion is realer than you think. Empty space isn't quiet. It's an ocean of hidden activity. Energy boiling invisibly. Virtual particles popping up and vanishing faster than you can blink. So we ask something deep. Why do calculations built on non-existence produce real results with stunning accuracy? Did the illusion become truth? Or do we still not understand what truth even looks like? If we look at where virtual particles show up, there are examples everywhere. Take the Casimir effect. Put two metal plates extremely close together in a perfect vacuum, and they get pulled toward each other. No magnets, no strings. The vacuum around us is full of virtual particles appearing and disappearing. Between the plates, there are fewer of them than outside. That imbalance creates a tiny pulling force. Scientists measured it. The results matched the math perfectly. Then there's Hawking radiation. Near a black hole, virtual particles appear at the edge of the event horizon. Sometimes one gets swallowed while the other escapes as radiation. Over time, the black hole slowly evaporates. We can't see this directly yet, but indirect measurements match predictions exactly, and virtual particles are essential to explain it. Even the sun depends on this. The fusion reactions in its core rely on force-carrying interactions. Virtual particles make those interactions possible. Without them, stars wouldn't burn steadily. They'd collapse or explode. These aren't philosophical ideas anymore. They're how reality actually behaves. So here's the debate. Virtual particles don't physically exist. You can't touch them. You can't see them. Yet, they control everything. Some physicists say they're just clever math tools. Others say they're closer to truth than anything else we have. History gives us a warning. Scientists once believed in the ether, an invisible substance carrying light. The math worked, but the ether wasn't real. Einstein showed it wasn't needed, but virtual particles are different. Their predictions aren't just close, they're precise to 12 decimal places. So we ask again, is this illusion actually part of cosmic truth? Philosophically, it gets even stranger. What does it mean to exist? Is physical touch required? Or is shaping reality enough? Abstract ideas sometimes matter more than physical objects. Virtual particles may be exactly that. They shape reality without existing in a traditional way. When quantum physicists study empty space, they don't find emptiness. They find activity everywhere. Quantum foam, particle pairs bubbling into existence, then annihilating each other instantly. This isn't speculation. Their effects have been measured indirectly. Think of air molecules. You can't see them, but you feel pressure. Virtual particles are similar, invisible individually, powerful collectively. Even at absolute zero, when all heat stops, quantum fields still vibrate. 0-point energy. Some scientists even think this relates to dark energy, the force accelerating the universe's expansion. The idea has problems, but it shows how seriously physicists take these math ghosts. Forces themselves work differently at this level. They're not smooth fields anymore. They're exchanges. Electrons repel each other by exchanging virtual photons. The strong force uses gluons. The weak force uses W and Z bosons. Even gravity might involve gravitons. This exchange model works with absurd accuracy. So why should this matter to you? Because virtual particles affect how materials behave, how radiation interacts with matter, how stars burn. Your phone, your computer, modern technology, all rely on quantum mechanics, and quantum mechanics includes virtual particles at its core. More than that, they sit at the edge of human understanding. They show us reality is stranger, subtler, and more beautiful than intuition allows. The vacuum buzzes, forces whisper through invisible exchanges. Existence itself becomes harder to define. Maybe the real mystery isn't whether virtual particles exist. Maybe it's why math works so well at describing reality. Why abstract symbols invented by humans match nature so perfectly. Are we discovering math or inventing it? Is reality fundamentally mathematical? Virtual particles sit right at that boundary. As we reach the end, we return to where we started. Thinking about how the universe might rest on foundations built from nothing, virtual particles reveal that emptiness isn't empty. That reality is shaped by things we can't see. They show us math can describe reality even when it talks about things that may not exist in any traditional sense. The universe blends the real and the virtual in ways language struggles to capture. For now, virtual particles are our best language for describing this invisible architecture. Whether future physics keeps them or replaces them, we don't know. What we do know is this: reality is stranger than we imagine, possibly stranger than we can imagine. And yet here we are, conscious beings, glimpsing the universe through equations and experiments, even if the foundation of everything is built from precisely calculated dreams. Sweet dreams of quantum foam and fleeting particles dancing in the void. Ghosts in the quantum machine, illusions that shape reality. And mysteries like this are why we keep looking deeper, calculating further, and pushing human understanding into the unknown.